Hey guys, all right, so we're going to continue today talking about using division to factor polynomials. We were just talking about all of the different theorems that we had, the remainder theorem and the factor theorem, that were useful with synthetic division. But here, this lesson, what we want to talk about is all of the ins and outs of how to just straight up approach a polynomial and then factor it using this division. There's one key ingredient missing, and that's what we want to dig into here. Okay, so I've got this polynomial that I want to factor, right? Let's say I already know one of the pieces. For example, factor this using some piece that we already know, like x plus 3. If you already know a piece, well, of course that bridges a big gap there. That means that I would put -3 in the box for my synthetic division, because that's what would zero out x plus 3. And then I would have my coefficients, the 1, 0, -7, and 6, because I want to account for all of my place values, right? 3, 2, 1, and none, 3, 2, 1, and none. Right? So then I do my synthetic division by adding, multiplying, adding, multiplying, adding, multiplying, and adding. And that's that key number. Remember, we were talking about, we really love to see this. We love to see that zero remainder, because that means it was an actual factorization step. No remainder, it's a full factor, right? So that means using this answer and the piece that we just divided, that x to the 3 minus 7x plus 6 is equal to x plus 3 times, and remember we're going to read this from the back end, remainder, number, x squared, so 1x squared minus 3x plus 2. Right? Now, fortunately, once you get to this point, you have something more recognizable left over. I could actually continue doing more synthetic divisions, but in this case, I don't need to, because I recognize that this is already factorable, and I can continue doing this. X plus 3 times x minus 2 times x minus 1. So, the key that's missing here is, how did I know the x plus 3, right? Our whole goal was to factor this polynomial, and I had magically knew this factor already. Okay, so that's where we want to get to the real theorems here. Okay, so this is a sample problem of what we're going to factor, but then let's write down a theorem here. Something that will help in this process. The rational root theorem. Okay? If you have some polynomial, p x to the n plus plus something, some number x to the 1 plus some number q. Okay, so I have some polynomial, and basically what I'm just trying to get at here is that this is just something with powers of x, right? P happens to be the number in front of the highest power. Q happens to be the constant number at the end that doesn't have any x's attached to it in your polynomial. So if you have some polynomial, okay, then a list of possible factors, and I'll put slash zeros. Okay, now zeros is another word for X-intercepts. Okay, can be formed by making patterns, by using the pattern. Factors of Q divided by factors of P. Okay? Now there's another little word that I want to insert in here. I say possible factors or zeros of the polynomial, okay? Of this polynomial here. And really, it's this word right here, rational. Insert that word rational right here in front of factors. Possible rational factors. All that means is I'm going to find a list of numbers. They may not all be correct, okay? But the list that I'm going to find will contain any numbers that I can use as factors and or x-intercepts. Now don't forget, when we're doing our synthetic divisions, right, the number in the box is an x value and the remainder coming out is a y value, right? So when I do some sort of synthetic division, right, do our zeros, we do our numbers, things like this, remember what we're looking for here is this remainder, okay? The number right here in the box, don't forget this is an x value, right? And the remainder is the corresponding y value that goes with it, right? So if we're talking about factors or zeros or x-intercepts here, then what we're talking about is a list of numbers, right? Any one of these things would cause this to be zero. The thing we were just talking a minute ago about being the real thing we're looking for, okay? So I can make a list of possible numbers that would cause this to happen in our synthetic divisions, basically. And they're going to be rational because I'm making fractions. That's what rational means. I'm just going to be building any possible fraction type number. Now, fractions can also be whole numbers because it could be something over 1, okay? But our list is going to consist of this. One extra little thing. They can either be positive or negative versions of these combinations, okay? Now, I say using the pattern, okay, factors of Q divided by factors of P. And that's going to just depend on these two numbers, the very end number and the very beginning number of your polynomial, right? That's what these are going to give me here. So I have the factors of one number and the factors of another, and I'm going to use all of those combinations, right? When I say pattern, we have combinations of this, okay? So let's take a look at an example here. By the way, you can look in the notes or in the textbook or whatever else if you want a better version of the actual rational root theorem. I'm just trying to break it down to what we're actually using it for here, okay? So be sure not to just look at this. Go read the notes, go read the textbook, look for that theorem. It's a big one. All right, so first example that we want to talk about we have is x cubed plus x squared minus 14x minus 24. Okay? Now, if it's equal to f of x, if it's not, whatever. I'll go ahead and put it equal to f of x for now. It doesn't matter. Either way, we're still having to factor this thing out or solve it equal to 0 or something like that. Okay? So here's the main deal. I'm not even going to pay attention to all of this middle stuff here. I'm only going to be looking at the very front number. This is the one that we labeled P in the theorem I wrote a minute ago. And this end number over here, 24, that's the Q, right? And yes, I know it's negative, but I'm really just focused on the 24, okay? So I'm going to list out the factors, right? Factors. Those aren't the list yet. The list is all about putting the factors together into fractions. But I need to see the factors. Well, factors of 1, right? It's just 1. That's it. Factors of 24. 1, 2, 3 goes into 24. 4 goes into 24. 6, 8, 12, and 24. Right? Those are the factors of 24. Okay? So whenever we're approaching one of these problems and I say, okay, let's make the list. This is what we're going to start out doing. Okay? So here's my list though. Here's my list. I'm going to take the factors of Q and divide them by the factors of P. Okay? All of the combinations that come from that. So we have 1 over 1. That's 1. 2 over 1. 3 over 1. 4 over 1. 6 over 1. 8 over 1. 12 over 1. Right? So I have 6, 8, 12, 24. And the theorem also said plus or minus. Right? So then negative 1, negative 2, negative 3, negative 4, negative 6, negative 8, negative 12, negative 24. And that's the list for this polynomial. Okay? It's made by doing combinations of the constant factors divided by the leading coefficient factors. Okay? Now, once I have this list, then the guessing game begins. Right? I have to find which one of these numbers really is the factorization number, the number that truly belongs in the box that gives us the remainder of 0. It may be more than one of them. It may not be. And it could actually be none. Every once in a while you'll find that. That means you've got a really crazy polynomial, and they probably won't give you one of those. Okay? At least one of these is going to work, though. At least one. And the good news of that, if you can get at least one of them to work, the x to the 3 will be broken down to an x squared, and all of those are recognizable to us either with a quadratic formula or old school factoring. Okay? But here we are. This is what the rational root theorem does. It gives us this list of possible numbers that we should guess. Okay? And on the bright side, what that is telling us is there's a whole lot of numbers we don't have to guess. I shouldn't have to guess 7. I shouldn't have to guess 9 or 12 or 13, right? In the last example, I magically knew to guess x plus 3, which was a negative 3 in the box, okay? What had happened was I had made a list and I guessed one of them and it was correct, okay? So that's what we're going to do here. We're going to pick one and we're going to try it and see, okay? So let's try, I don't know, something like, let's try 6. Yeah. So I'll put 6 in the box. Now don't forget what that represents is I'm factoring out an x minus 6. Okay? But I'm picking 6 from the list here. And that's the factor that it represents. This represents x minus 6. Then I'm going to do my synthetic division. 1, 1, negative 14, negative 24. Put my 0, set up my division. Okay? So add, multiply, add, multiply, add. So let's see, 42 minus 14 is 28, right? Then multiply, so 120 and 48, 168, and then add. I mean, you can pretty much tell by now, I'm definitely not getting a 0 here, right? Let's just finish it out. It's going to be 144, okay? So, this one's a fail, right? It's a bust, and that's what you want to see sometimes. I want to know which ones are good and which ones are not good. I just hope that I find one of them that works before I find too many of them that don't, right? However, don't forget, we have the remainder theorem. This isn't a total loss. even though I did not get a factor, which is what we really want those x-intercepts and those factors, it's okay, I still found one little small piece of information. I did find out that f of 6 equals 144. I wasn't exactly looking for that piece of information, but I can still use it to my advantage later on if I were ever graphing this or doing something else with the function. So this does tell me that f of 6 equals 144. So on the function would appear the point 6 comma 144. Right? Probably too big for our graphs, but still important information for that function. Okay? So then we would continue guessing. Right? Let's say we guess 4 this time. Okay? So then I would put my numbers 1, 1, negative 14, and negative 24. Set up my division again on the polynomial because I haven't broken it down any. So I still have the same original numbers. So 1, multiply, add, multiply, add. I'm an idiot. 4 times 5 is 20, David. And that gives me 6. 4 times 6 is 24. 0. Yes. Right? Success. The 0. That means f of 4 is 0. But more importantly, I found a factor. Don't forget what 4 represents. That's x minus 4. I've started the factoring process now. I have broken this thing down some already. Let's annotate what that is. So I don't need these little factors here anymore because I've got my list. Right? I've got the original polynomial here. And let's see what we've done so far. Right? What we've gotten so far is that f of x also now equals x minus 4 times, remember how to read this, this is remainder number x squared. So that's x squared plus 5x plus 6. Okay? Well, like I said before, good news. You've broken it down to something that's probably recognizable. The x squared plus 5x plus 6, you can probably factor it right now. Let's use that knowledge, though, and guide another guess, because I want to show you something. See, when you're doing synthetic division, you don't have to stop. If I know, or if I think I know, another good guess, or maybe I just want to try another guess, you don't have to go back to the original numbers. It's just like in factoring. If I was going to try factoring this further, I wouldn't go back up to the original polynomial and try to break off a different piece. That wouldn't make sense. I've already broken it down some, right? I'm not going to go to a candy bar and try to take a different bite off of a spot that I haven't bitten yet. I'm going to continue working on the same spot. It's the same thing, okay? So right here, I would continue factoring this piece if I were doing it the normal old school way. Well, it works with synthetic division also. I don't need these numbers anymore. I've factored a chunk off, and these numbers right here will work just as good. So if I try another guess, right? We can see the 5 and the 6 here, probably something with some 2's and 3's. Let's say we try negative 2, okay? Watch this. I can put another box right here. Because look, there's my numbers right there, 1, 5, 6. And I'm just going to build off of it again. Or, if you don't like that, you can rewrite the 1, 5, 6 somewhere else. That's okay. Either way, I put the box next to these numbers. I can put another 0, draw a shorter line, and do another synthetic division. 1, negative 2, 3, negative 6, 0. Okay? And at this point, I can realize that I'm done. Because the thing that I have left over here is just an x and a number, and that's going to be prime. Right? Let's write down and see what we have here. Negative 2 in the box, don't forget that represents x plus 2. And then just looking at the answer here, remainder number x, this is x plus 3. So look, in one little chain of synthetic divisions, I've got my complete factorization, x minus 4, x plus 2, x plus 3. Or, you could have gotten that same thing from here. Either way, the final factorization, x minus 4, x plus 2, and x plus 3. In most of these problems, then, it would ask you to list something further. Now that you've got the factorization, it would also say, hey, this is a function. What are your x-intercepts? Okay, fine. Guess what? We've got most of those too. Those are the numbers in the box. My x-intercepts are x equals 4 and x equals negative 2 so far. But I've got one more. I've also got the x plus 3 piece. Whatever makes x plus 3 0 would be negative 3. So I have those x-intercepts. And I want you to note that all three of those appear in this list, right? We've got the 4, we've got the negative 2, and we've got the negative 3. They are actually in the list. So we would have eventually found them if we would have exhausted the list, okay? So that's how synthetic division is going to really help us here. Once you find one or two of these especially, it all just falls apart. And then not only do I get to list a factorization, but I can turn that factorization also into important points on a function. Okay? Flip side on that, on the wording on this, if this wasn't a function and just an equation, like equal to 0, instead of x-intercepts, we would have just called these solutions, because they would be making it equal to 0. Right? So it all is working the same way. They could be asking you to solve an equation, they could be asking you to graph or factor a function. It's all the same stuff. Okay. Let's try another one. X cubed, let's do g of x is equal to x cubed plus 11x squared plus 35x plus 25. All right? So we have this one now. And remember, the instructions are going to be factor it out, find x-intercepts. And then later on in other chapters, it'll be things like graph it and things like that. We've got a few other things to talk about before we do that. But, okay, so the instructions here would say something like factor and find x-intercepts. Okay? Factor and find x-intercepts. Well, remember when we approach one of these polynomials, if I'm going to use synthetic division, I need some sort of list to guess from. And how do we make that list? I'm going to break down the first term and the last term, the P and the Q, right? Right here, what are the factors of 25? And right here, what are the factors of 1? Right? Factors of 1, just 1. Factors of 25, 1, 5, and 25, right? Those are my factors. So to make my list of guesses, right? I would have to do Q over P. So that's 1 over 1, 1, 5 over 1, 25 over 1. And then also, don't forget, we can do all the negatives. So that would be negative 1, negative 5, negative 25. Okay? Now, since it ends in 25, probably one of our best guesses is definitely going to be either the 25 or the 5. A good conservative guess would probably be the 5, right? Okay. Here's another little trick, a little hint that I could show you. Do you see how everything is positive? Well, remember the way synthetic division works. I'm going to set up something in the box, right? Put something in a box, and then my numbers are going to be 1, 11, 35, 25. Since they're all positive, remember the way I'm going to do this synthetic division is I'm going to be adding and multiplying, right? Well, the more I add, if I keep getting positive after positive after positive, this is just going to keep getting bigger. I don't want that. I want something to zero out. So we need some negatives in there. Since these are all the same sign, I definitely want to pick something negative in the box so that it will start subtracting. Okay? So in this case, a good first guess would probably be -5. Right? Let's put that in the box and see what happens. Let's see. I'm going to add, multiply, add, multiply, add, multiply. Sure enough, 5 panned out, worked great. Or -5, I should say, right? Not 5, -5. Okay? Notice the end number again on this one, right? This is going to be x squared plus 6x plus 5. It ends in 5 again. That tends to make me believe that I could actually do something with 5s again. Okay? Here's the thing. Just because last time you saw me cross something off the list, that was when it failed. In this case right here, it's very possible that a number could work more than once. All that means is you'd have the same factor twice. Okay? And we can look at this a couple of different ways. Look at what we have so far. The -5 here represents x plus 5, right? And then I've got x squared, 6x, and 5. So right now, this is where we're at. Right? This is where we're at in our factorization. I can still factor this further, okay? And I think you can see where we're going with this. The two numbers that multiply to 5 and add to 6 are 5 and 1, right? Well, notice right here in the box, I could do -5 again. And you can do that whenever you want, right? -5 technically hasn't failed yet, so I'm not taking it off the list. -5 in the box again, put another 0, draw a line, 1, right? -5 times 1 is -5, add, get a 1. -5 times 1 is -5, get a 0 again. It worked again. That's the same factor twice in the same polynomial. Plus, it's finished. Look, it's x and the numbers left over. Let's write down our pieces here now. I've got x plus 5 once. I've got x plus 5 again. And then here at the bottom, I've got x plus 1. So my complete factorization of this function is x plus 5, x plus 5, x plus 1. But remember, we typically don't write things like this over and over and over again if they happen multiple times. Okay? We tend to write it more like this. X plus 5 squared times x plus 1. Now this brings up an important other term here. Okay? Anytime you have a factor, okay, the number of times that that factor is used is called a multiplicity. Okay? This is the number of times a factor appears. In a factorization. Okay? Shorthand for that, the exponent on a term, right? The exponent on a factor. The multiplicity of x plus 5 here is 2. The multiplicity of x plus 1 here is 1, right? In this case, the multiplicity is equivalent to the exponent on the factor. And that's something that's going to help out a lot later too when we're graphing these things. The multiplicity actually tells us something about the shape of the graph as well. Okay? So that's important to keep in mind for later. When we're factoring these things out, if something succeeds, it's completely possible that you could do it again. And it would succeed again. That can happen, as case in point here. Okay? Now, we're almost done, right? What are the x-intercepts here? Well, they're in the box, right? -5 is an x-intercept. And then I also have to look at the x plus 1 here. What intercept would make that 0? My x-intercepts in this case are x equals -5 and x equals -1. Okay? Now sometimes when we're listing out x-intercepts, by the way, x-intercept, don't forget, the word 0 is also synonymous with that. X-intercepts or zeros. When someone's listing these out, they may also give the multiplicity with them. X equals -5, multiplicity 2. X equals -1, multiplicity 1. Now, if they don't list multiplicities, that just means all of them are 1 probably. Okay? When they start listing multiplicities, it usually implies that one of them probably is higher than 1, like 2 or 3 or 4. Okay? Otherwise, they would just give you the x-intercepts if they didn't have multiple uses. Okay? All right. Let's keep going. Let's grab another example. So let me word this one a little bit differently. How about just solve? 0 equals, and let's do x to the 4th minus 9x to the 3 plus 8x squared plus 60x. Okay? Now here's another thing. Synthetic division is great. It's a great new addition to our factoring family, but that doesn't mean that you have to throw everything else that you've ever done with factoring away. If you approach a problem, take a step back sometimes. Do I always have to do this new trick? No. Look at this ring really, really close. I'm going to be factoring to solve, because that's usually how we solve equations that have higher powers of x. Factoring is a very powerful tool with that. Do you notice they all have an x in common? There's nothing easier to factor than a GCF. Let's start there. I don't even need division or anything else. I can just start myself off, boom, with getting one factor out of the way, because it's just a GCF of x. Right? This is directly equal to x times x to the 3 minus 9x squared plus 8x plus 60. Immediately, with x being a factor by itself, I've already got one of my solutions as x equals 0. I then can continue with solving this equation. 0 equals x to the 3 minus 9x squared plus 8x plus 60. Okay? So I've already gotten one solution. Multiplicity 1. The x is only used one time by itself, right? So, as a factor, it has a multiplicity 1. All right, so now I've got to continue solving this. And I have that number on the end now, right? There's my q. And my p, again, is 1. So let's make a list, right? We've got to do the factors here. Right? Let's make a list. We've got that 1 in the front here. So it's going to be everything over 1 again. Okay? Kind of same old thing. What are the factors of 60? Well, we have 1, 2 goes into 60, 3 goes into 60, and it just helps. Just keep counting up, right? 4 goes into 60, 5 goes into 60, 6 goes into 60, 7 doesn't, 8 doesn't go into 60, 9, 10 goes into 60, and if you'll notice, as soon as I hit that 10, I'm noticing 10 times 6 is 60, right? So basically I've gone over the hump. Everything else is just going to be the leftover of those other multiplications. The next one will be 12, because that's times 5. The next one times 4 will be 15. Then times 3 would be 20. Then times 2 would be 30. And of course, times 1 would be the number 60 itself. And then don't forget in our list, we could also do all of the negatives. -1, -2, -3, -4, -5, -6, -10, -12, -15, -20, -30, -60. Right? Okay. A lot of guesses there to knock this thing out, right? Okay. So we just jump right in. And notice this time I don't have all the same sign, right? I've got a negative in there. So it is possible that I can pick something that's positive or negative this time, right? Well, let's start on the low end. Let's start with 1, let's say. Right? Let's put in 1 in the box. Then I've got my numbers. 1, -9, 8, and 60. Put my 0, draw my line. Add, multiply, add, multiply, add, multiply. Oops. Oh well. Don't forget, this gives me a piece of information about the function, right? Of course, we're not really graphing anything. This is just an equation, okay? Plugging in 1 gave me a positive 60, okay? All right, well, let's keep going. Let's try 3. Right, let's try 3. 1, -9, 8, and 60. 0, draw the line. 1, 3, 6, -18, -10. 3 times -10 is -30. And then 60 and -30 is 30. Still no good, right? Still no good on that one. So let's continue to guess here. Let's see. Notice though, when I went from 1 to 3, 60 went down to 30, right? So if you think of it like function values, I went further in the x, right? X went from 1 to 3, and the y value went down. So it's possible that if I keep pushing in that manner, that I'll run into something good, right? So let's see. Let's try, let's go really far this time. Let's guess 6. 6. So 1, -9, 8, 60. 0, draw a line. 1, 6, -3, -18, -10, -60. And voila, there we are. I just had to keep going far enough in the x's this time. Now, it's not always that way, but you can use those input and outputs to sort of give you a roadmap of where you're at sometimes, right? So 6 worked. Don't forget, what that means is I've just found one of my solutions. So x equals 0 was a solution. Now x equals 6 is also a solution from the box here. Good news, 1, -3, -10 now are my new numbers that I'm working with. This is now what I'm going to be dividing to find the rest of my answers. Okay? Also good news, that's a squared, right? Remainder, number, x squared. If I exhaust this list and none of them work, if still none of them work, I'm in good shape still, okay? Because the last resort, this is a quadratic, x squared. If I have to, I can solve that quadratic formula, right? So one way or another, I'm going to get the last 2 number answers out of this equation because I've gotten it to that squared structure point, okay? Or if you like old school, bring it back out, x squared minus 3x minus 10. See if you can break it into something that will factor, right? Okay, so next guess. Let's try -1. Well, let's see, it's got a 10. Let's not do -1. Let's do -2. -2. Notice I'm not building off of the division like I did before. And that's okay. I could have put the other box here and gone further down. I just don't feel like keep going down because it's harder to see. But notice I'm copying those numbers. That's what I'm working with now. And my new guess is -2. So 1, -2, -5, 10, 0, and that one worked, right? So notice that what I have here is that x equals -2 is a solution now also to this equation, right? So in the solving portion, I've got 0, 6, and -2 as solutions. We should have 4 solutions though, right? And remember, there's still one more factor waiting here. This one is x minus 5 as a factor, right? And technically, what I want to do with that is like what I've been doing the whole time. I want to solve x minus 5 equals 0. That's going to give me x equals 5. Okay? So I've got my 4 solutions here. And if I had to write out the factorization, right, I could easily do that as well. Look, right here, let's continue our little factorization tree. I had x to begin with. Then x equals 6, that's x minus 6 as a factor, right? X minus 6 comes from the box. Then over here, -2, that's x plus 2. And lastly, I actually have the factor x minus 5 is left over, right? And then I've also, from that, I can easily read my solutions. 0, 6, -2, positive 5, just like I have them circled around here. Okay? So notice I wasn't dealing with a function this time. It was an equation, and I was just solving it equal to 0. Same math, right? Where a function is equal to 0 is called X-Intercepts. Where an equation is equal to 0 is just the thing that we use to solve when we're factoring. It's all the same stuff. Okay? All right, let's try another one. Let's try one that's got a different leading coefficient this time. Let's say factor, right? F of x is equal to 3 x to the 3 minus 8 x squared minus 5x plus 6. Right? Okay. So again, noticing that front number is different. And we're being asked to factor just like as we did before. So I'm going to go through making the list. Right? Remember the list, I need these factors on these numbers, right? The factors of 6, 1, 2, 3, and 6. The factors of 3 are 1 and 3. All right. So here's the list. Don't forget, the list is all about making combinations and patterns with these factors. So I'll have 1 over 1, 2 over 1, right? That's just like before. 1 over 1, 2 over 1, 3 over 1, 6 over 1, right? And then, of course, the negatives. So that's negative 6, okay? Also, though, I've got something else to make more combinations with, more patterns. I can do 1 over 3. 1 over 3. I can do 2 over 3. 2 over 3. 3 over 3 is 1. I've already got that one. 6 over 3 is 2. I've already got that one too. So then I just need the negatives of these. That would be -1/3 and -2/3. Okay? So then I've got the complete list for that polynomial here. All right? Don't freak out. There are fractions in there. And a lot of times what that means is probably one of those is actually one of my X-intercepts, one of my factoring combos that works. Okay? My advice, exhaust the whole numbers first. Those are easier synthetic divisions. Not by much. I mean, the fractions aren't bad, but they are going to be simpler with the whole numbers. And the factors are easier to write from the whole numbers. I try to save the fraction ones for the very last if I can, right? If I can. I may not have to use them at all if I can do that. So let's just hope we guess really, really well. Okay? Let's start with, I don't know. Let's start with 2. So there's 2. I've got 3, -8, -5, 6, right? So I'll do my 0, draw my line. 3, 2 times 3 is 6, then -2, then -4, that's -9. 2 times -9 is -18, so I got -12. Okay, so that one's a bust. But I did find out that f of 2 is -12. That helps sometimes. Let's do another guess. Let's guess 6, right? Yeah, let's guess 6. 3, -8, -5, 6, 0, like this. So I've got my 3. 6 times 3 is 18. That gives me 10, then 60, then 55. 6 times 55 is 330. So I've got 336. That was way off of 0, right? But I want you to notice something. I did this on purpose to demonstrate something to you. Do you notice that f of 2 equals -12, but then f of 6 equals positive 336? That means that as x went along between 2 and 6, y went from negative to positive. It did this. What does that mean? Somewhere in between 2 and 6, hopefully, we would find one of our magic 0 numbers. Now, does that guarantee that it's one of the ones in the list? No, because there's a lot of numbers between 2 and 6. But if this happens to you and you notice that your y value switches in between 2 of the x values like that, switches sign, the y value switches sign, try guessing in between them. So in our list, what's between 2 and 6? 3, right? So that'll be my next guess. I'll guess 3. 3, -8, -5, 6, 0. Draw a line. 3, 9, 1, 3, -2, -6, 0. Lo and behold, this one did actually work out, right? Again, that's not a guarantee, but this is a strong indicator right here. When you go between 2 x values and the y value switches sign. That's because we deal with continuous functions, things that have to be all connected, okay? All right, so I've got one of them to work, right? And so from here on out, I'll be using 3, 1, -2, okay? So, right here, my next guess, I'll just go ahead and spoil it. Let's go ahead and guess the -1. 3, 1, -2, 0, this, okay? So 3, -3, -2, 2, 0. Okay, so let's write down what we have and talk about the factorization real quick. Okay, over here we got x minus 3 from this division. Right here we got x plus 1 from this division. And the leftover right here is 3x minus 2 from the leftover part of that division there. So we have our 3 factors. It is a cubic, so we should expect 3 factors, right? And also we're going to have the 3 x-intercepts. I want you to notice that my x-intercepts are x equals 3 that we found, x equals -1, right? And then if I set 3x minus 2 equal to 0, right? Add 2, divide by 3. Notice I would have gotten 2/3. And again, 2/3 is in our list. So it would have eventually been found, one way or the other. Okay? So all of our possible rationals, and if it's going to be a rational x-intercept or solution or whatever, it's going to be in that list. Okay? Let's write out the factorization to finish this out. F of x would then be equal to x minus 3 from this first bit times x plus 1 from the second one, and then the 3x minus 2 from the last one there. And this would be the factorization, right? Along with the x-intercepts would be convenient. Okay? All right, so at this point, oh yeah, let me note again. Notice these are all multiplicity 1, right? Multiplicity 1, multiplicity 1, multiplicity 1. Use that word more and more so you can get used to hearing it and seeing it. Right? Let's switch gears now. The next example, what I want to show you is some of the ones that don't come out quite as nice. And I say quite as nice, they're still about the same amount of work. Don't fret over that. But also don't expect every single time for these answers to always be the whole numbers and the numbers in the list. The rational root theorem gives you the possible wholes and fractions, but not every polynomial is going to guarantee that it has those. Okay? So here's the thing. Let's do this one. Solve 0 equals x cubed minus 8x squared plus 15x plus 4. Okay? Okay, so seems harmless enough. All of the numbers there are whole numbers, right? Okay, let's go with it. Let's make our list. Right? The list of guesses. We're going to look at our beginning and ending numbers again, right? What are the factors of 4? What are the factors of 1? Right? Factors of 1 is 1. Factors of 4, 1, 2, and 4. Okay? So then subsequently my list is going to be 1, 2, 4, negative 1, negative 2, negative 4. Because I'm just going to do the combinations of all of these over 1 basically. And then the negatives to go along with it. Okay? All right. Out of this list, only one of them is going to work. You can go through this entire list, okay, and absolutely only one of them will work. In this case, it happens to be 4. Okay? So let's say you go through the list and you go through several divisions, you know, and you try them and you keep failing, no go. Eventually you'll run into doing the division of the 4, right? If you do them in order, well, it would only be your third division. That's not bad, right? Because these go fast. 1, negative 8, 15, and 4. 0, draw my line, 1, 4, negative 4, negative 16, negative 1, negative 4, 0. Okay? So then let's write out what we've got here. From this, I now have 0 is equal to x minus 4, that's the thing in the box, right? Times this thing down here is x squared minus 4x minus 1. Okay? Now naturally, from here, we've already got x equals 4 as a solution, and we knew that already because 4 was the number in the box when it zeroed out, right? So we already knew that solution. I want you to look at the other one. That's why I wanted to write this out, so that you could notice that this is not factorable. Okay? From your old school factoring, you need to recognize there are not two numbers that multiply to negative 1 that add to negative 4. Okay? Or, if you didn't recognize that, you would end up dividing out the whole list and only succeeding once, right? This time. All of the rest would be fails, which you would get a lot of information about the function, that's fine. But then you'd be like, well, wait a minute, I only got one answer, and I'm supposed to have 3. So that's where this next bit comes in. Like I was saying a long time ago, once you get to that quadratic stage, right, you're home free no matter what. Worst case scenario here is, I still have to solve this is equal to 0, right? That's the split that I'm doing here, basically. x squared minus 4x minus 1 is equal to 0. And I have a quadratic formula for that. So that's our last recourse here. I will be able to solve it if it's at a quadratic, but I may have to use the formula. Oh well, right? So here we go. From this right here, x equals negative b plus or minus square root b squared minus 4ac all over 2a. So then I get x is equal to 4 plus or minus, I've got 16 plus 4, right? Square root of 20 all over 2. Okay, now don't forget, square root of 20, I can break that down, right? Square root of 20, let's do that off to the side for a second just to be sure. This is all I'm doing. Square root of 20 is the square root of 4 times the square root of 5, which is just going to give me 2 times the square root of 5. So that's the simplification I'm going to do here. This is going to be 4 plus or minus 2 square root of 5 over 2. Now I notice that I can do 4 divided by 2 and 2 divided by 2. If that's the case, you should. So instead of writing it this way, I'm going to say 4 over 2 and 2 square root of 5 over 2, because that's easier to notice that I can simplify that. So I have x is equal to 2 plus or minus the square root of 5. Okay? And that's 2 separate answers. Let's write them out. Instead of plus or minus, it's x equals 2 plus the square root of 5 or 2 minus the square root of 5. And there's my other 2 answers to this equation, right? I had x equals 4, and now I have these other 2 answers, 2 plus the square root of 5 and 2 minus the square root of 5. Side note, I want you to note that these are conjugates. Conjugates. That will always happen when you are solving the type of polynomials that we solve. If one of them is going to be irrational, like a square root of 5 or something like that, it will always have its conjugate buddy with him as another answer. Okay? So if someone says, hey, I've got this quadratic or I've got this polynomial, and I know one of the answers is 9 minus the square root of 7, you know automatically, oh, well, then 9 plus square root of 7 is also one of the answers. Okay? So anything that's irrational like this, in the polynomials that we solve, they're always going to be in conjugate pairs like that. Okay? So if I've got one, I'm going to end up with the other one too. Okay? Overview of this problem. This is where the factoring stopped. So if someone asks for the factorization, there it is. Okay? However, they also want you to solve equations like this. So I've got x equals 4, and then I had to solve the rest of it with the formula, and I've got my other 2 answers there. Okay? Let's try another example, just like this one. F of x is equal to x cubed plus 7x squared plus 9x plus 63. All right? So, in this one right here, I'm noticing that I could actually do this particular factorization with grouping. Notice if I took a 9 out of these two, right, I would have x plus 7. And if I took an x squared out of here, I'd also have x plus 7. So you can actually do this one all old school if you wanted to. Okay? Let's go ahead and get the practice making the list and things. Right? Okay, so with the list, remember we've got to do our factors. Right? Factors of 63. 1, 7, 9, let's see, also 3. Let's do them in order. 1, 3, 7, 9, 21, 63. Then over here we got our lonesome old 1 again. Right? So then pretty much like as usual, a lot of times I'm hoping that you've noticed by now, when we have that 1 in front, our list pretty much is given by the factors on the constant n. So 1, 3, 7, 9, 21, 63, negative 1, negative 3, negative 7, negative 9, negative 21, negative 63. Okay, so from before, like I said, I was noticing, right, that when I factor this out, I get an x plus 7 here and an x plus 7 here. Also, I'm noticing that they're all positive. So when I'm doing my synthetic division, I'm going to want to pick a negative so that it will do the right thing with the subtraction. Okay? All of this to me is pointing towards try the negative 7. So that's what I'm going to do. Negative 7 in the box. I have 1, 7, 9, 63, 0 over 1, negative 7, 0, 0, 9, negative 63, 0. Right? So it definitely worked out. But again, notice every once in a while, just take a glance at what you've got left over. Here I've got remainder number x squared. All I have is a 1x squared and a 9. X squared plus 9. So if you think back to your factoring days, that's not factorable. So let's write down what we've got here. F of x, when I factor it out, is from the negative 7, that's x plus 7, times x squared plus 9. Right? So that's factored out there. Obviously, I can get this x-intercept here, right? That's going to be x equals negative 7. Or don't forget, x-intercepts are also called zeros, right? So I've got that one right away. But I'm obviously missing two other ones, okay? And this is actually where a good distinction between x-intercepts and zeros is going to come in. Because this is the only x-intercept that we're going to find, right? And I'll show you why in a minute. That's the only x-intercept we're going to find. However, we're going to find 3 quote-unquote zeros to this function. And that's because a 0 is technically any number that causes this to be 0, whereas an x-intercept implies a point, right? So look, I've got an x-intercept of x equals negative 7, but as far as zeros go, I'm supposed to have 3 of those. Negative 7 is one of them, and then the other 2 are not in the x-intercept list, right? They're going to come from over here. So I've got the x plus 7 comes from there, but I still haven't finished out this piece, right? X squared plus 9 equals 0. Okay? And there's several different ways you could go about solving that one, but let's go directly. That's going to be x squared equals negative 9, or if I subtract 9 from both sides. And then I'm going to square root both sides. So x would equal plus or minus the square root of negative 9. Well, don't forget, a square root of a negative number is imaginary. Square root of 9 is 3. So square root of negative 9, I'm going to get x plus or minus 3i. And that's why they don't appear in the x-intercept list, because these don't appear on the x-axis. However, they are accepted values in mathematics, therefore they can still be listed as quote-unquote zeros. So I would put 3i for one of them and negative 3i for the other one. Okay? And that's truly the only difference between a 0 and an x-intercept here. Most of the time they're synonymous, but if you happen to have some zeros that are non-real, complex, imaginary, whatever, then they won't also be x-intercepts, obviously, because we're not graphing in the complex plane. Okay? All right. Now, one more problem. Let's work in reverse here. Okay, and this is actually where we need to start building up to that final section where we're going to bring all the information about polynomials together, factor them, find the intercepts, graph them, do all that stuff. Okay, so there's one more example here that I want to talk about before that next lecture. Okay. Construct a polynomial with zeros as follows. Okay? So we have x equals 1, x equals -2, and x equals the square root of 11, let's say. Okay? Okay. And we want the x equals 1 to have a multiplicity of 3. And all the rest of them multiplicity of 1. Okay? It sounds complicated from this end. But remember, whenever you're doing the synthetic divisions, the number in the box is the 0 that we get. And those always can be built into the miniature factors. Okay? So right here, I'm going to start with f of x, right, equal to, and then right here, x equals 1. Well, x plus 1 wouldn't work, right? Don't do this. 1 plus 1 is 2, not 0. You want them to zero out. So it's x minus 1. But wait, it said multiplicity 3. Easy. Cube it. Right? 3 of them. Next, x equals -2. Remember, we want it to zero out. So I would put x plus 2. Right? That's this piece. And multiplicity 1, right? To the 1 power. And then there's this last piece. Don't forget, a couple of problems ago, I gave you a little hint. Anything that's irrational like this has to come in a conjugal pair, right? So if I've got negative square root of 11, okay, it doesn't ask for it, but I must put negative square root of 11. And that one, okay? It didn't ask for it, but for the polynomials that we do, all of those have to come in conjugate pairs. So if I have a positive square root, I'm going to have the negative that goes with it. If I have a positive I, you saw in the last problem, 3i, I'd have negative 3i. Okay? In one of the other problems, we had 2 plus the square root of 5, so we also had 2 minus the square root of 5. In this case, I'm taking the object that I see and just also including his conjugate. So I've got 2 more factors here. I'm going to have x minus the square root of 11, and I'm going to have x plus the square root of 11 from these 2 things here and here. Okay? So then the only thing from here is just going to depend on what your instructor or grader or computer program, whatever, wants your format to be. Okay? On certain tests, I'm fine with letting students leave it in this format because it's all about construction. Other places, like computer programs and things like that, they may actually want you to multiply these out. So just keep that in mind. Okay? All right, I hope this was helpful, and stay tuned for bringing it all together.